Hey everyone, so in this video I'm going to go over the beginning of factoring for you. So the first question says, well the do now says explain the process you would use to subtract 4x squared minus 3x plus 2 from negative 2x squared plus 4x minus 7. Now the key word here, if you remember from the last lesson, is the word from. And when you see the word from, you switch the order. So we're going to put this first, then subtract this, because you're taking away this is coming out of that. It's coming out of it. Okay, so I would say that I would put negative 2x squared plus 4x minus 7 first in my subtraction problem. And then I would subtract 4x squared minus 3x plus 2 by distributing and changing all the signs. Distributing the negative, let's do it that way, the negative, and combining like terms. Okay, so in this lesson we're going to talk about factoring. And the reason why we talk about factoring after lesson 4 is because in the previous lesson we talked about multiplying polynomials. And what factoring is we're undoing the multiplication. We're trying to find the two factors that create the polynomial that you see in front of you. 2 or 3 or more. It could be more than that. So the first two that we're going to go over in this lesson is GCF and DOTS. So first we're going to talk about GCF, which stands for greatest common factor, which means that you're trying to look for the greatest common value that is between the terms of the polynomial. So for number 1, I noticed that I have 6x plus 3y. Now the first thing I always look for is I look for if there are any letters that are in common in the two terms. This is term 1, this is term 2. Term 1 doesn't have any letters that term 2 has. This is x and this is y, so letters aren't in common, but there might be some factors in the numbers. So sometimes I will use a factor tree. I know 3 times 2 is 6. I also know 6 times 1 is 6. And 3 times 1 is 3. So I can see here that 3 is a common factor. And since 3 is the common factor and it's the biggest common factor, that's called my GCF. My GCF right now is 3. So let me rewrite the problem. Back in Algebra 1, what you would do, some of your teachers would do, is they would divide each term by 3 to see what would be left over. So in this case, when I divide 6x by 3, I get 2x. And then when I divide 3 by 3, I get 1, so it just becomes y. Now please don't forget that this 3 that you divided by needs to be on the outside. The reason why it needs to be on the outside is because theoretically you would have to be able to go back to the original because you're trying to make an expression that's equivalent to the other one. It's just that this one's factored. So this would be the factored form, and this is the simplified. This is the standard form. So you want to be able to go back and forth between the two of them, therefore you can't forget about your factors that you're pulling out. So if I was to factor this guy, I would have this. Next one, again, I'm going to ask myself the question, are there any letters that are in common? And there are. There's an x here and an x squared here. This has just a single x, whereas this one has 2 x's. Okay? And the greatest amount of x's I can pull out is 1x because they each have 1. I can't pull out 2 because this guy right here only has 1x. So I know my GCF so far is an x. Okay. Now for the numbers, I know that 3 is 3 and 1. I know that 3 times 1. 27 is 9 times 3. It's also, actually 9 times 3, well there's 27 and 1. But here I can see that the 3 is what's common. So the 3 is a part of my GCF. So like the previous problem, I'm going to take my expression and I'm going to divide by my GCF. So I will divide this thing by 3x. Now when you divide 3x by 3x, anything divided by itself is 1. Okay? When I divide 27 by 3, I end up getting 9. And when I divide x squared by x, I end up getting x. And remember to pull that 3x on the outside. This is my answer. Now, if you're having trouble with the idea of why this turned into an x, it's because of this. There are technically two x's here. Oops, let me just write this a little bit better. There are technically two x's with the x squared over a 3x. And what's happening is you're dividing. So when I divide x squared by x, you're canceling out that extra x. You could also remember your exponent rules, that when you divide, you subtract. So 2 minus 1 is 1x. Next one. Okay, so I'm going to look for my letters, and I'm going to see, okay, this has an a, this has an a squared. This only has one a, and this has two a squareds. But the most I could take out from both of these is 1. So that makes my greatest common factor have an a in it, because the biggest amount of a's I can take from each of them is 1. Remember, you have to, the thing I remember is that you have to be fair. Whatever you take from here, you have to take from here. You can't take more from here than here, otherwise it won't balance out. So I can only take 1 from here, therefore I can only take 1 from there. This guy here has a b squared, he has a b cubed. The highest amount of b's I can take from him is b squared. That means that's the highest I can take out from here. Even though he has 3, I can't take out 3 from him because he only has 2. And you can think of it this way. If you were divided by b cubed and you thought that was the GCF, this wouldn't work out because there's more b's on the bottom than there are on the top. So that's why the GCF for the b's is b squared. So I'm going to write b squared here. I'll look at my numbers. 2 is 2 times 1, and 4 is obviously 2 times 2. So the GCF will be just 2. Okay, so that means I'm going to divide by 2ab squared. Okay, I'm going to divide by 2ab squared on both of these. Take one at a time, don't go too fast. So 2 divided by 2 is 1. I don't have to write that though. The a divided by the a, that'll cancel out. So these guys kind of cancel out, this cancels out, and the b squared cancels out. When everything cancels out, it doesn't become 0, it becomes 1. Minus 4 divided by 2 is 2. And a squared divided by a, there are 2 a's on top and 1 a on bottom. 2 minus 1 is 1. So I got a. And then there are 3 b's on top, 2 b's on bottom. 3 minus 2 is 1, so I'm going to put a b here. And again, don't forget to write that GCF on the outside, because remember, you want to be able to eventually, you could prove that this goes back in and gets the original problem. Okay, so for the next few examples, I believe we start to recall dots. Let me just make sure I did all the ones that are there. Yeah, so dot stands for the difference of two squares. So let's write this out. Dots. The acronym stands for difference of two squares. Squares meaning perfect squares, okay? And remember, the definition of a perfect square is a number that has two factors that are exactly the same. So for example, 4 is a perfect square because it has factors of 2 and 2. 9 is a perfect square because it has the factors of 3 and 3. 16 is 4 and 4, and so on. So the ones that have factors that are the same exact number that multiply to that number. With letters, it has to be an even number because it would be x times x. That's the same exact thing, gets you x squared. Another example would be x to the 4th. X squared times x squared, that would get you x to the 4th. So you need two factors, two things. So two things meaning two terms, meaning a binomial, and you need them to both be perfect squares, and also subtraction. So the first thing I asked myself is this a binomial? And yes, I can see that because there are two terms. And I then asked myself, well, is this a perfect square? Yes, it is, because this is x times x. Is this a perfect square? It is. It's 3 times 3. And the big thing is this subtraction? And that is subtraction. So because it's subtraction and we have two perfect squares, what we're going to do is we're going to split this up. And basically what we're doing is we're going to undo the box method that we did in last lesson. I'm going to redo the box method so you guys can see how it goes back to x squared minus 9. This is going to go here, and this is going to go here. And the reason why it goes first is because it's the first term here. So notice I'm making one binomial split up into two binomials, but I'm putting the x in the first place because it's the first place in the other guy. Then I'll put the 3's here because they're the second piece of the binomial. and then always make sure it's opposite signs. And that's how you factor using dots. Now just to preview that it goes back to its original, if I undo this, I would have to do the opposite of factoring. Remember, factoring is just like division, because what's happening is you're breaking this up into two separate pieces. So the opposite of it to do my check would be multiplication. So I would go ahead and check with the box method. And you can see here this gets you x squared, 3x, minus 3x, and negative 9. And if you notice, these are the same terms but opposite signs, they cancel. That's why it has to be a minus 9. It has to be subtraction for dots because otherwise this canceling will not happen. So if you have no subtraction, it's a no-go, it's not dots. Okay, next example. Again, I'm going to ask myself, is this a binomial? That's correct because there are two pieces. Are these perfect squares? Yes, because this is a times a, this is b times b. So two things that factor into this that multiply to the same thing. And then, yes, there's a subtraction sign. So usually when I set up dots, I always make sure I have my parentheses and my plus and minus. Then I split up the first term, and then I split up the second term. And there you go. That's your dots. Okay, same deal. The only thing different about this one is that there's a number in front of the first term. So the same rule applies. This whole thing has to be a perfect square. And it is because 4 is 2 times 2, and x squared is x times x. So it does give us that perfect square definition of two terms, two factors that are exactly the same. Okay, so I'm going to split this up again, but plus and minus. It doesn't matter where you put the plus or the minus because remember the commutative property allows you to switch this order because it's multiplication. Okay, so I'm going to write my first term 2x here and 2x here because again this is the first term, so it goes in the first term spot of these two separate binomials. And then the factors of 25, that would be perfect, are 5 and 5 because 5 times 5 is 25, and boom, there you go. Okay. All right, so now what's going to happen here is you're going to look at this and say, oh, it's a binomial. There's a subtraction symbol, and I see a squared here. But this is not a perfect square. 5 is not a perfect square. The factors of 5 are 5 and 1, and those factors are not the same number. The factors of 15 are 15 and 1 and 5 and 3, and neither of those combinations are going to give me the same exact two pieces. So this is not dots. So we always need to ask ourselves before we even try anything is if I can pull a GCF out. And there is a GCF here, because between 5 and 15, I can divide by 5. That means I'm going to pull my 5 out to the front. I'm going to be left with a squared minus 3. Now you should always ask yourself when you factor, can I do more? Sometimes it's multi-step. And the reason why I'm asking this specifically is because this has a squared, which has the potential to break up into two pieces. And it's starting to really look like dots because I have, remember, difference, that's subtraction, of 2. Yes, there are two pieces, squares. And I do have a squared here, but this is not a perfect square because it's just a 3. So I can't factor that out anymore, and this is my fully factored form. Next one. I'm going to ask myself, GCF. There is. I can pull out an 8 out of these two pieces, and I can also pull out an A because they both have 8s and A's inside of them. The 8s will cancel here, leaving you with an X, the 8 and the A, minus 56 divided by 8 is 7, and then the A's will cancel out. Just do not forget to write that GCF on the outside. Okay, moving right along. Where are we? We are right here. Okay, so to do this one, I'm going to think, is there GCF first? That's always what your first approach is going to be. You can think of the letters first, you can think of the numbers first, but it's whatever you prefer. Now, I'll do the letters first because the numbers here are a little bit larger. So I see an x and an x squared, so I can only take out an x because I can only take out the greatest amount of x's that I can possibly pull from both of these. And the biggest amount I can pull is one single x. And it's the same with the y's, because this is a y squared and this is a y, so I can only take out one single y, because the second term here, the biggest amount of y's you can take out is a y. Now, with 36 and 48, there are large numbers here to deal with, and if you know your times tables, which you should realize that these both have a factor of 12 in them. This is 12 times 3, and this is 12 times 4. And that is the biggest number you can pull out, 12. You can notice that because 3 is like a prime number. So I would divide each of these by 12. But there is a calculator trick on how to get the GCF if you're not sure of what it is, especially between two numbers. It's called GCD. So let me just mess around with my calculator so I can go through the steps here. So I'm just going to pull my calculator up. Okay, so what you would press is math on your calculator and then go over to num, just like how you're getting absolute values. And you would see a command that says GCD. And then you would, in that GCD area, do 36, 48. And when you do that, the comma is underneath the sign, S-I-N, on the calculator, and you should pop out with a 12. So that's the trick to get the GCF with a calculator. So I'm going to divide this, and I'm going to end up getting 3. The x's will cancel. I'll get a y minus this will divide by itself and get 4, and then these will get you a single x, and these will cancel out. And then I'm just going to remember to pull out that 12xy, which was my GCF. Again, you should ask your question, can I do more? This is a binomial, but none of these have squared, so it's completely simplified. And 3 and 4 don't have any common factors inside of it, because this is only 3 times 1, and this is only 4 times 1 and 2 times 2. The only other thing you could pull out of here is a 1, but that's pointless because it just isn't going to change the problem at all. Okay. Alrighty. So, next one here is another GCF problem. And the reason why is because, yeah, this is a perfect square because it's AB. The factors, you can split it up into AB times AB. But this is a plus sign, and for dots we need subtraction, and this is a single term, it's just A. So the only thing I can do here is a GCF, and the only thing I can pull out is A from this one, because that's the only thing left, and A from this one just because you have to be even on each term, and that's the greatest thing you can take out of this binomial. And I'm going to pull that A out. A squared divided by A is going to get you single A. B squared plus, this will cancel out, not to 0 but to 1, because something divided by itself is 1. Okay, next one. I don't see subtraction, so it's definitely not dots. Remember, dots stands for difference of two squares, so it's most likely another GCF problem here. So between 20 and 25, you should remember that the GCF here is a 5. There's r cubed here and a single r here. So the biggest amount of r's I can take out is 1, because that's the amount I can take in the second one here. Remember, you got to be fair. Here there's 2 s's and there's 3. So I can only take out s squared because that's the highest amount I can take out of this one. It's pretty much with the letters the smallest amount that you can take out, because I mean it's the greatest amount you can take out in the fact that it's the biggest amount you can take out of this one, but between the two of these two things it is the smaller s value, if that makes any sense. Alright, so now I'm going to do 20 divided by 5, which is 4. R cubed divided by r is just r squared, and then these will cancel. Plus 25 divided by 5 is 5. The r's will cancel. S cubed divided by s squared is going to get you just s. And then I will pull out that 5r(s) squared, because you have to make sure you have every single piece. And you can always check if you distribute back in to see if you get the original. And you do, because 5 times 4 is 20. R times r squared is r cubed. S squared times this is just s squared. 5 times 5 is 25. R times nothing, well that's r. S squared times s is s cubed, so that does check out. Last question of this lesson. It says Jerry factored x squared plus 9 as x plus 3 times x plus 3, because 3 times 3 is 9. Do you agree with him? Why or why not? Now, with this whole lesson, we should say disagree, because this is in dots. There's a plus sign here, okay? And since there's a plus sign here, it's not going to factor into this. Seems like it, because we know that 3 times 3 is 9, and x times x is x squared. But when you actually box method this out, what you would want to happen is you would want the middle term to cancel out, like how I showed you guys before. But what happens here is when you do x times x, you get x squared. You get 3x here as well, and 9. And things are looking pretty good for Jerry because the x squared and the 9 are there, just like he said. But if you notice, the 3x's are not opposite signs. So since they're not opposite signs, you can't cancel them out. So they would actually result in x squared plus 6x plus 9, which is a trinomial. The only way something's going to cancel out is if these guys are opposite signs. But you can't have them be opposite, because if it's negative 3 times 3, it's a negative 9. And Jerry doesn't want that. He wants positive 9. So this doesn't factor into this. No, it factors into this. So you would say, do you agree with Jerry? No. And the reason is because x plus 3 times x plus 3 becomes x squared plus 6x plus 9. The 3x's don't cancel when multiplied out. Okay, and that is this lesson. So I hope this helps you, and I will see you guys soon.